This is an example of velocity and acceleration diagrams, and we will also include the inertia forces for one of the links on the diagram. So what we have is a 4-bar linkage system shown on the screen. I have previously worked these out on a separate sheet of paper, drawn my diagrams roughly with a ruler and calculated all the values. So what I'm going to do in the video is just sketch the diagrams, but the shapes will be roughly correct. So if you want to do it, your diagrams should look like that. If you are just interested in how to draw them, you can pick that up from the sketches. So first thing we need to do is to draw the velocity diagrams for these. In this 4-bar linkage system, we know the angular velocity of link AB in here, and we know that it's doing 100 RPM. So A is my fixed point, so we know where that is. The next point on my linkage system will be the point which is driven from that, which in this case is B. Since it's a link, I know the velocity of B will be at 90 degrees to the link, and I know that since it's going clockwise, then my velocity will be this way. Labeling, it is the velocity of B because I drew it at B. So it is the velocity of B relative to the other end of the link, in this case A. So it is VBA. VBA is equal to omega R. Omega will be 100 RPM over 60 times 2 pi times 0.3, the length of the link, which is equal to 3.1 meters per second. So if we draw this now on my diagram, again you would draw this to scale. This would be 3.1. It is the velocity of B relative to A. In terms of the subscripts, the arrow always points to the first letter. So sometimes people put a little arrow on here to remind them that the arrow is pointing to the first letter. So my arrow is pointing down and to the right, so therefore the arrow is pointing to B, and therefore this must be A. So that's my point B. My next point on a linkage system, the next point will always be joined to two other parts of the link. In order for the link to work, you have to hold every point by attaching it to two other points. In this case, C is joined to B and C is joined to A. So we need to find those velocities. Since BC is a link, we know that there will be a velocity here, velocity of C, because I drew it at C. The velocity of C relative to B at 90 degrees to the link. For CA, this one, I know that the velocity of C, drew it at C, relative to A, will be across here. Now I haven't put any arrows on these. I don't want to try and predict them. I'm just saying that it's in that direction. Could be up that line or down that line. So if I take VBC, let's take this one first. VBC must pass through B and C, and I know where B is. Therefore, on my diagram, I can put this line through here. So this we said was VBC, and now if I do VCA, this will pass through C and A, and I know where A is, so I can put a line through here. So this point where these cross must now be point C. We labeled these vectors. Up here we labeled them VCB. VCB will be an arrow going between C and B, so this one will be VCB, and according to our naming system the arrow will point to C, so the arrow is going this way. I might just take this off because that looks like it's an arrow. This is VBA. This vector, on my diagram up here, we said it was VCA. So I'm going to label it the same, VCA, and we know that the arrow points to the first letter, which is C. So this is my velocity diagram completed. From that, I can scale those. I can work out that this one is approximately 3.0 meters per second, and VCA is approximately 2.3 meters per second. Next on here, we will draw the acceleration diagram. We're going to follow the same sort of steps as we did in the previous diagram. Logically start with A, it's the fixed point, then start with B because that's the driven point in this case. In terms of accelerations, we always have two accelerations, a centripetal acceleration and a tangential acceleration. I'm going to start my diagram, if you like, and I'm going to go, this is point A, it's a fixed point. So the next point we want to find is B. B will accelerate centripetally back towards A. This will be a centripetal of B, because I drew it at B, relative to A. It will also have a tangential, or potentially have a tangential, AT for tangential, of B relative to A. In this case, that's going to be 0, because the question hasn't said that it's accelerating, so we can assume that this is rotating at a constant velocity of 100 RPM. So, in terms of my diagram, I need to calculate the lengths. AC of BA is equal to VBA squared over radius BA. From our previous diagram, VBA was 3.1 squared over the length of that is 0.3. It's going to come out to 32 meters per second squared. What I would normally get people to do is to draw this vector. So on the diagram, the little arrow here was the same as this one. We labeled it AC of BA. Again, the arrow points to the first letter, so we know B will be here and A will be here. So this label is attached to that. Therefore, I can now draw this vector over here. So here's A. Whoops. Here's A. We can draw this. This is AC of BA, and we said that B was at this end. So this is the location of B. Same as before, we now need to find point C. Point C must be joined to two other points. C is joined to B, and C is also joined to A. So I need to use those relationships. Therefore, from C, I can put in relative to B, I can put in a centripetal acceleration, AC of C, because I drew it at C, relative to B. It will also have a tangential acceleration. I don't know whether it's up or down. AT of CB. If I now look at C relative to A, C will accelerate back towards A, centripetal acceleration of C relative to A, and there will be a tangential acceleration at 90 degrees to the link, AT of CA. So lots of bits of acceleration, lots of accelerations to count for. So the ones that I can calculate are always the centripetal accelerations. C of CB is equal to VCB squared over radius CB. So from our velocity diagram from the first part of the video, 2.3 squared over 0.7 gives me 7.5 meters per second squared. And I also need the centripetal acceleration for C relative to A will be equal to V squared over the radius, which we said would be somewhere around 3.0 squared over 0.45, the length of CA, which will give me 20 meters per second squared. So now we need to draw these and basically look for where the lines cross, so we can draw in the things that we know, which are the centripetal accelerations. So I'm going to start with CB, this one here. The centripetal acceleration of CB is across this way, and it's about 7 long. So this is AC of CB. Arrow is pointing to the first letter, and therefore it's going away from B, if you like. So C is somewhere out in this area somewhere. Once I draw the centripetal acceleration, the immediate thing you do is put on the end of that a line which is the tangential acceleration. So my final answer is out there somewhere. If I now look at C relative to A, C relative to A is 20 meters per second, and it's in this direction. Let me sketch that into here. This is AC of CA, so arrow points towards C somewhere and away from A. Immediately after you draw the centripetal, you now draw the tangential one at 90 degrees to that. Where those two lines cross must be where C is. So my tangential acceleration is here and here. I can now write those in terms of labels. This is AT of CA. The arrow we said must point to the first letter, which is C, so my arrow is going this way. This one we said was ATCB, and again the arrow points to the first letter. So that's largely our diagram. If you like, then I can actually put in this. This is the link BC itself in here, the sum of the two parts. That's largely our acceleration diagram, and you can get accelerations from those. What we will do is carry on now and start looking at forces on the links due to the inertia of BC. So BC has a center of mass halfway along its length. So halfway along this point we labeled a point G, and we're going to put that as the center of mass. If it is halfway between BC on this diagram, then it will be halfway between B and C on this diagram. So this will be my point G. The acceleration of G, absolute acceleration of G, will be the value of G relative to A, which is pretty much a straight line through here. Whoops. This will be the acceleration, in this case, of G relative to A. Now, in this case, it does just overline my lines. In most cases, it probably wouldn't. I can now draw that back onto this diagram. So this is my acceleration of point G. So that's my absolute acceleration of G. from my diagram here, I can scale the length of this. So the acceleration of g relative to the fixed point I had as 3.8 meters per second squared. Okay, if I want my link BC to accelerate that way, then obviously I need to subject it to a force here in order to make it accelerate in that direction. That's only the linear part of my acceleration. Link BC is also angular acceleration, so we need to sort out which way that is. Now I can easily do that if I have a look at link BC. This is just my link BC point G on here. What we have previously worked out is we have worked out the tangential acceleration of C relative to B. This is it here. And we know that the arrow was pointing downwards. Therefore, this link has an angular acceleration going clockwise at this point. My angular acceleration I can calculate. Angular acceleration is equal to AT over the radius, so just dealing with the tangential part. From my diagram I can measure off the length of that from the acceleration diagram, and we worked out that is 9 divided by the length of the link, which is 0.7, and that gives me 12.9 radians per second squared as my angular acceleration. So to make this link accelerate this way, then what I have to do is offset my force to this side out here somewhere by a value of eccentricity. So now my force is being applied to the right of the center of mass. This will cause my link to have an angular acceleration in a clockwise direction, which is what I need. Next trick is to work out how much that eccentricity is. My angular acceleration, torque, is equal to inertia times acceleration. My torque will be given to me by my force times my eccentricity, must be equal to I alpha. As a separate little calculation, what I do know from the linear part is force is equal to MA. My force is equal to the weight of the link, which we said at the beginning was 3 kilograms, times the inertia of, acceleration of G, which we said was 3.8 meters per second. That's this one up here. This will give me a force of pretty close to 11.4 newtons. So I'm going to put this back into here. 11.4 newtons times my offset is equal to the I value from the start of the question, 0.12 kilogram meter squared, times my angular acceleration is 12.9. Gives me an eccentricity of 0.136 meters, or equal to 136 millimeters. So now, next part again has to be on a scale diagram. We are going to offset this 136 millimeters, and we have a force going down through here of 11.4 newtons. Okay, if we now just look at link BC, link BC is going to be a 3-force system. There is the 11 newtons that I need to provide here. There will be a force at B and a force at C. In terms of linkages, link AC is just a standard link and it's not being driven. Therefore, link AC can only support tensile and compressive forces. So the force on this link has to be in this direction, either compressive or tensile. The force that I'm trying to generate is this 11.4 newtons through here. This must be therefore my concurrent point. So if you go back to basic mechanics, we are told that if three forces act on a component, then those forces will either be concurrent or parallel. Concurrent meaning that all the forces must pass through the same point. Therefore, if that's my concurrent point, then the force at B must be along this line in here. So this will give me the angles of my three forces. This is my force B, this will be my force C, and this is my MA force. So we can now draw a separate force triangle. So here is my 11.4. This is the force that I need to make my link accelerate. This will be given to me by adding up the other two forces. Force C and force B must equal this. So again, if I take my parallel lines, force B, if I draw force B back through here, draw force C back through this point, this will be force B, therefore this will be force C, and we know that that force plus that force must equal that force. So force C will be down, force C will be down this way, force B will be down that way, causing a total of 11.4 newtons going in this direction. Again, if we draw those to scale, approximately I get force C is equal to 6.0 newtons and FB is approximately 12.5 newtons. Okay, those will sort out your forces on pins B and C. If you need to know what the torque is in terms of my driving link, then that's relatively simple. We've just worked out that force B will be 10.5 newtons. Therefore, I can get this distance at 90 degrees and work out a torque. So I roughly calculated this at about 170 millimeters. Therefore, the torque at A would equal force times distance. 10.5 newtons times 0.17 meters will give me a torque of about 1.8 newton meters at A in order to deal with the inertia force for that link. And that's the end of the example.